Hello everyone, and we're continuing with this video to talk about the primitive data types and how we represent data in the Java programming language. We're going to continue with the int or integer based types where we left off, and the last thing we did was we wrote about writing or declaring variables, and we mentioned the requirements for valid variable names, meaning variables that do not cause errors in our language. We said there were two main rules we needed to follow. The first being that a variable name must start with a letter or underscore, and the letters could be uppercase or lowercase. And then the second rule was that after that first character, a variable name must only contain letters, numbers, or underscores. So you'll have a mix of different things like that. And then we mentioned a standard, which again is not a requirement, but is a rule that we typically follow because it is what most Java programmers do to make things easier to deal with, to read across different people's code bases. And we talked about camel case, where the first word is lowercase and every subsequent word in the variable name is capitalized. And if there's only one word, then it's just a lowercase word. So let's go ahead and start and declare an actual variable. And we're going to make one of each type that we talked about. We talked about byte, short, int, and long. And they're all representing integer values. Int is the most common one. That's the one that we're going to focus on. That's the one that the AP exam cares about. But we'll declare one of each type just to see that those keywords do exist in our language. So let's go ahead and start with byte. Now I'll mention when it comes to variable names, many of the variable names I'm coming up with as we do our examples in these videos they're arbitrary names. They don't mean anything, but typically when you create variable names, you try to make them meaningful to the context of what you're doing. If your system is focused on weighing atoms or molecules in a chemistry environment, then you would probably name variables that are related to that. So weight of molecule, number of atoms, num of atoms, things like that. Things that have meaning to you or make your intent clear in your code. We can always put comments, but if we have good variable names, then it's not so difficult for someone to quickly glance at your code and see what you meant to do or have an idea of what the overall domain is. If we just call our variables x, y, z, 1, 2, or I, j, k, things like that, it becomes much more difficult to diagnose what is wrong, to diagnose what the purpose is, things like that. And so generally speaking, we try to put meaningful names. So my names might seem kind of silly and random, but as we aim for particular goals in our projects, the names do matter. And so my names will not be a complete mess, but more so to practice the standards and the variable rules or naming conventions. So let's go ahead and make a byte variable. So again, a declaration is first a data type, and then the name of the variable. We're mapping a label to some location in RAM that can hold some amount of data. So let's hold a byte value. So byte is the data type, and notice it turns kind of an orange. Before the red error occurred, we did see that kind of orange color, and then as soon as I have a variable name, it should hopefully clear up. And so I'm going to go and call this small number. And there it is. And so we'll point out the data type is byte, and there's that first thing. And then the name is small number. Notice I follow the standard. Small number. Small is one word. It starts with a lowercase s. Number is the second word in the name, and it starts with a capital N. So I'm going to go ahead and, just as a note, go ahead and put valid and standard, because I'm doing both, making a valid variable name and a standard variable name, because I am using camel case. So let's go ahead and try another one. Let's go ahead and say short another num. And again, valid and standard, right? I have a data type that is short, that's correct. Another num is following camel case. Another is one word. So now I say word, and even though num is maybe not necessarily a complete word, the idea is that if you're intending to make individual words, we often kind of cut down words to save space. You still try to follow the camel case standard. So another num is another decent variable name. Let's try a third one. Now we're going to use int, so something like count of students. And we can see that the count of students is also camel case, so valid and standard. Let's go ahead and try making a valid variable, but one that is not standard. So let's go make another integer. I'm going to stick with int again. So I'm going to say int, let's say duck count. And so notice I used an underscore. I'm allowed to have underscores in my variable name according to rule number 2. So as long as it starts with a letter or an underscore, I can have letters, numbers, or underscores in the name. But it is not standard because I do not use camel case. So I'm going to say valid and not standard. Now again, a standard is not going to break. Oh, I forgot my double slashes. Not following standard is not going to break anything, but it is potentially, depending on where you are, it could cause problems with people that you're working with or other scenarios when it comes to variable declarations. So duck count. Let's do a long. And a long is a very large number, so we'll say long, really big num. And again, camel case is what I am following. And so there are four types, and those are all 5 declarations. Again, a declaration is not a giving of a value, not an assignment of value, but just merely stating to the compiler, I need you to find this many bits worth of space in RAM when the program begins so I can store data eventually. And that's important because we cannot store or use variables without them being declared. We'll see eventually when we get to assignment, the storing of values, if a variable has not been declared, it cannot be referred to or used in any meaningful way. That is one of the requirements of variables. It has to be known. As opposed to, let's say, math, if we're just writing formulas, I can choose to put y or x in my formulas just because I chose those names. And now, typically, we still aim for a purpose. Usually, if there's a variable in a formula in mathematics, it's because it has a purpose or a meaning. But still, the name is not important, or the assumption of why it's there is not really questioned. Here, it cannot be used unless it is already declared at some point. And there are many rules about declarations, and we're not there yet, but we will eventually see. Sometimes we can make variables without any problems. Sometimes we have to be careful with the names. And there are a lot of different scenarios. So these are our primitive integer data types. Int is the one that's the most important to us. That's the one that we care about the most. So I think that's enough for integers. We can move on to similar primitive data types, still in the realm of numbers, but a little more complex because they allow us to hold real numbers or are the closest approximation to real numbers that we're probably going to get. And so we're going to move on to that. So I'm going to go ahead and put an end. I forgot to do this for myself. I'm going to go ahead and put this part right here and mark this information as purely about variables, but the data for integers was up here, right? So this was the integer category. Still all primitive data types, and we're going to continue with the primitive data type. So our next data type that we're going to talk about is primitives. So data type is with real numbers or decimal or fractional numbers. This is an issue because hopefully we recognize first the set of real numbers is also infinite. Just like the integers. There are an infinite number of integers. There's an infinite number of real numbers. There is a difference between these types of infinity, and in the future you may have discussions in more advanced math courses about this, but the general premise that we'll take from this is that the integer numbers, while there are an infinite number of them, you can always order them in a way that makes it clear that you will not miss an integer number. Right? So if I'm at the number 7, I know what goes after the number 7. It's the number 8. I know what goes before the number 7, the number 6. There is no confusion. If you pick an integer number, I can tell you the one that's before and the one that's after, whether it's positive or negative. You give me negative 32, I know the next number going more positive would be negative 31. The more negative one would be negative 33. The idea is that it's a definitive ordering to our numbers. Unfortunately, with the real numbers, that is not possible. If you have a decimal number, you can continually make an infinite set of decimal numbers that are before it. If someone gives you 2 decimal numbers, you can come up with a smaller decimal number that fits between them. This is uncountably infinite. There's just too many, and there's no meaningful ordering that we can easily establish. And there is a famous proof of this concept that you might hear about in the future. And so I'm not going to go too much more into detail. But the key is, unfortunately, we must limit how we represent real numbers. We can't have everything. Another issue is irrational numbers. Right? Everyone knows pi or e as irrational numbers, numbers that have a potentially infinite number of decimal or digits after the decimal place. How can we represent that in a computer that has physically limited amount of RAM? If they're infinite decimals and we had infinite RAM, then maybe we could do this forever and ever and ever. But conceptually, that's not possible, at least with physical limitations that we're aware of today, or that I'm aware of today. And so we have to cut it off somewhere. We have to establish that. And so the data types we're going to talk about are in the category of real numbers. What they're often called, so before I put data type, I'm just going to mention this. Real numbers in computers are often I guess, specified as, well, we'll call them floating point numbers in computers. And so what does it mean to be floating point numbers? And again, this is a really complex topic, and we're not going to focus on every detail because we're not computer engineers. We're not worried about architectures of CPUs and things like that. The takeaway we have is that essentially we have to come up with a formal way to write decimal numbers that can be understood by the computer. We have a limited number of bits to use, and so what we do is we take advantage of the fact that sometimes we need more digits after the decimal, sometimes we need more digits before the decimal. And so the idea that what we keep track of floats or adjusts based on the number, whether it's more whole or more fractional, that can be changed kind of behind the scenes or automatically managed by the computer, and this is to our advantage. So we can hold a lot of numbers, and we can hold them to a certain degree of accuracy. So this real floating point numbers are not so much about the exact number, but how accurate can we be to a decimal number. And so the two types we're going to see, the only difference between them is their variance in accuracy. And the second one that we're going to see is the one that's more accurate and the one that's used in Java by default, and is the one that the AP exam is concerned with, right? So floating point numbers allow us to represent real numbers in a roughly accurate way. So the first floating point data type we're going to talk about is called float, and it is based on that word. And so what we'll say is float is often also called single precision floating point number. Number. And so floats are 32 bits in size. And that seems like a reasonable amount, but because of the way we have to represent both a whole number and a fractional portion, we don't actually get to hold 32 bits worth of value. Instead, we talk about accuracy in terms of the number of significant figures we can represent. And so if you think about what a significant figure is, maybe you remember from your science courses when you do scientific notation, a significant figure typically is a figure that if you were to remove it from the number, you would change the value, and that's a dangerous thing. So often and quickly, I'm not going to go over all of it. You can always ask your science teachers if you need more details. But essentially, if you have a leading zero, a zero in the front of a number, it's not significant because if you take it away, it changes nothing. If you have zeros at the end of a decimal point, you can drop those as well because typically they don't change the value. They might change the way we say something. So for example, I'll write out an example of it. If I gave you the number 1.00 or 1.01000, let's do that. 1.0100. How we would say this number is 1 and 1, we could say 1 110,000ths, right? Because this would be the tenths place, hundreds place, thousands place, 10,000ths place. So we could say 1 in 110,000ths. But if I did this, the value does not change, but what we say changes. So this is 1 and 1 100th. It's the same thing. They're equivalent in value. No data has been lost. So would you consider the last two significant? I would say no. And again, if that's maybe incorrect, it's not so important. What we're kind of take away is that generally we're aiming for accuracy of the representation, and this is as accurate as we need to be. We don't need those extra 2 zeros. It's still the same value. And similarly, if I did this, that does not change the value of the number. That is still the number 1 in 100, 1 in 100. So there's no change. And so it's important to recognize that significant figures are the key to representing accuracy, particularly in scientific notation. And so floating point arithmetic and floating point precision is based on how many significant figures we can get. So with that said, we will say floats typically have an accuracy of between 4 and 7 significant figures, which is not bad, but is also pretty limited. 7 significant figures at best is really not that accurate. If you have super small numbers, that kind of falls apart quickly. Or really large numbers, it also kind of stops to not be very helpful. If we want a lot of decimals, it kind of decays, and we can't get a very small number or accurate number that way. So float is not a bad option, but it's still really not used. And again, it was limited in size. The goal was to not have so much. Older style software might use float, and depending on what libraries you use, some libraries that blend with Java or use the Java language may use float. For example, the processing programming language, which is based in Java, which is a fantastic library for visuals, often uses float as the default value for its numbers, its decimal numbers. But that can cause inaccuracies in visuals, and so we won't be working with float very much. The second version is essentially the same, but with more accuracy. So our second version is going to be called a double, and this is the one that matters to us. This is the one that AP Exam is caring about. It's essentially the same thing, but what we would say is it is a double precision floating point number, and this is 64 bits in size. And what that boils down to is that doubles typically have an accuracy of 14 to 17 significant figures. And that's significantly more, right? That is a big jump forward. That is a lot more accurate, and that is very helpful. And that's usually enough to handle most scenarios. The fact is, even for example, computing things that require the number pi, having 17 significant figures of pi is usually enough to get a very, very, very accurate calculation. We don't really need more than that. And if we have to, then maybe you would have to come up with another way of doing it. But that's usually enough for most scenarios. Same with E, right? The natural number. 17 significant figures is a good amount. And so again, for our purposes, we're holding real numbers. I also mentioned that according to the people that write the language Java, they suggest one scenario that you might think that doubles and floats are helpful is for currency, for money, because we use fractional parts, right? You can have $0.37 or 37 cents. But they suggest because of the way it's internally held, it's not a good idea to use doubles or floats for currency. And we'll see some solutions to that later on. But they are correct that that's maybe one scenario where it might seem like a good idea. We wouldn't do that. It's more for decimal numbers, fractional numbers that we care about. So let's go ahead and declare some of these values. So let's make a float. Even though we're not going to use the type, it is not a bad idea to try writing it out. So float, I'll call it decnum or decimal num. Again, the name is not too important. I am following the standard, and it is a valid variable name. Let's actually try making a variable name that is not valid. This is something I didn't do before, but I should have done it. So let's try it now. So let's make a double, but let's give it a name that does not work to prove, because I mentioned these rules about it must start with the letter and number, but I didn't really show it. So let's validate that this is really the case, because I don't want you to take me at my word just because. Instead, we can prove it by writing code that either fails to compile or doesn't or works, and so that way we know. So for example, let's say we're trying to represent the percentage of bacteria in a petri dish that survived for more than a day with some kind of antibiotic. I don't know, something like that. Right? It's going to be a percentage. It could be a very small percentage, but it's going to be a decimal number or a fractional number at some point. So one name I might want to use is something like % survived. And immediately we get an error because the percentage symbol in our language, the syntax of our language says you cannot use the percentage symbol like that. And if I read the error, it's not going to be 100% clear. It says not a statement, semicolon expected, not a statement. And that's not that great of an error to clarify, because this symbol has a mathematical meaning that we haven't gotten to yet, and it can cause problems if we try to use it as part of a variable name. That is unacceptable. So this does not work. So what I'm going to do is I'm going to put a note, not valid, even though it might be standard because it at least has only one word lowercase, but it's not valid, so it does not matter whether it's standard. So I can't leave this around because then my program will not compile. So what I'm going to do is I'm also going to comment out the line. So I'm going to put 2 slashes in front. I'm going to leave it here so we know that it's no good. But we recognize that we can't leave it on there because it would be an error, right? So let's do a correct version. Maybe we could do something like double % survived. And that is a I didn't mean to put the comment. So that is a reasonable name. It is correct. It can still hold a decimal number, but it is a valid name, and it is a standard name. I'm going to go back quickly to our integers, our whole number types, and let's try making one that's also broken. And let's do something like int. Imagine if I have a system that's used at a school, and I need to keep track of the number of senior students that are over the age of 18 because they're allowed to leave school early without parental permission or something like that. And so you might want to have something like 18 or over count. That's not an unreasonable variable name. So I could write something like 18 or over count. It's not going to work because the number 1 is not a character, is not an underscore, so this fails to work. So I'm going to, again, mark this as not valid. Right? So we cannot do this. It will not work. And again, if we read the error, it's the same kind of strange, not a statement, semicolon expected, even though there is a semicolon here. It's complaining about the number itself. It doesn't understand how this connection happens. And so we're going to have to comment this one out. What would a better name for this be? We could do something like int count over 18s. Something like that, right? So now, or num seniors over 18. I mean, there's all kinds of names that we could do to represent. Again, the name would give away the intent, and then it has to be valid, and then standard would be just convenient. I would say this is standard because count is lowercase, over is capitalized, and 18s is not a word. I mean, it is, I guess, a word, but it's not letters, so 18s is perfectly reasonable, right? We can't put an apostrophe because that would not be a valid character because it has to be a letter or underscore or number, right? And just as a last one, I'll go ahead and do this, even though it's maybe not standard, but we could get away with this. We could do something like int underscore 18 or over count. And that would work. So either one of these would be a solution. If you really wanted this name to be something like that, then a solution would be underscore. Again, now would it be standard? Now we could argue about that because the first word is lowercase, the second word is capital, the third is capitalized. But does it underscore as part of the name include as a standard? That's debatable, and to me, that doesn't matter so much. I don't think people would be picky about it. If I quiz you, I'm not concerned about underscores. It is focused on the capitalization of each subsequent word. And again, 18 is a word, but it's not with letters, so it doesn't have to be capital. You can't capitalize the number 18. Right? So we'll come back to down here, and it's the same concept. We have to be very careful that we follow those rules for variable names no matter what the data type. Okay, so I think that we've done our integer values, so primitives for integer values. Int is the most important one. We've done our real or floating point numbers, and double is the best type for that. So we're going to stop this video here, and then we'll continue in the next video with a few more data types, and that video will pretty much finish up our data representation in the primitive realm, so the easy ones that are stored in RAM directly. I'll see you in the next video.